Welcome to the video presentation of the TVCG invited paper Influence Maximization with Visual Analytics, a joint work by the VIS group at TU Vienna and the University of Perugia. First, we will go through some basic definitions of information diffusion and influence maximization. Then, we will describe in detail our contribution, the evaluation, discuss its result, and conclude the talk. In social networks, individuals' decisions are strongly influenced by recommendations from their friends and acquaintances. This happens in both direct and indirect ways, through a mechanism often known as the word-of-mouth effect. In such a context, a subset of individuals acting as influencers or seeds will promote an idea with the chance of influencing other individuals in the community. We can model this environment as a weighted directed graph, with the weight of each edge being the influence that one node has on other neighbors. Higher influence means a higher chance of influencing that specific neighbor. Several diffusion models have been introduced. In this example, we show the model known as independent cascade, in which each new activated node will try and influence their neighbors once before remaining silent. Within this context, influence maximization is defined as the problem of finding an arbitrary small subset of nodes such that the final influence spread, that is the number of activated nodes, is maximized. It is known to be an NP-hard problem. Moreover, each diffusion process is stochastic. This means that for each process there are many potential instances, requiring multiple simulations in a Monte Carlo fashion, making, in turn, more difficult to evaluate the spread of any seed set. In visualization literature, there is little research about information diffusion and influence maximization. Existing research focused on the visualization of VR diffusion processes backed up on some other data facets, such as geographical context, or onto the visualization of a single simulated process onto a network, exploration of the visual steps of a process, and a graph layout that is aware of the diffusion process underneath. However, none of the existing approaches support the comparison of different seed sets after different conditions, nor allow the user to inspect and eventually modify the simulation seed set. It is within this context that we present VAME. It is a visual analytics system that has 4 clear design tasks: simulate a diffusion process under different models and seed selection algorithms, evaluate each seed set based on its quality, spread, and the impact that the network structure has, compare different seed sets and simulations to understand which are the activated structures, which are the eventual parameter effects, and the final influence spread, and finally, feedback, that is, modify the seed set with the objective of improving the spread or activating a specific area of the graph. This can be made completely by the user using existing heuristics or assisted by the system itself. This is a snapshot of the system. We will discuss the details of each individual view in the following. As anticipated, VAME is a visual analytics system based on a multiple coordinated view approach. It supports different levels of details, and it targets diffusion model designers and, more in general, information diffusion and influence maximization researchers. We evaluate our system with 2 case studies and 1 questionnaire about the value of visualization, following the IST protocol. We discuss now each of individual design tasks of the system. First, we begin by simulation. Out of the box, we implement 2 of the most common diffusion models in literature, namely the independent cascade and linear threshold. We also include 2 seed selection heuristics. The simulation engine runs within the application server, and to improve scalability, we implemented the models directly in Neo4j graph database cipher language. To evaluate the performance of each seed set, we provide different views. We include basic information about the diffusion process, such as the number of seeds, the average activation rate per simulation, the standard deviation, seed selection heuristic, and diffusion model. Here, we show the number of node activations over time as a box plot. The heat map visually shows the overview of the current state of the diffusion process. The color encodes the average fraction of active nodes per cell at the current time step, while the numbers show the same metric but at the end of the process. This feature can be controlled with a button in the interface and can be enabled for best and least, like in this case, performing cells. The local topology can be inspected by brushing a set of cells of the graph in the density matrix. This view highlights the currently active nodes and edges, with a color transparency encoding their activation probability. Finally, by hovering on a node in the local topology view, its activation probability is displayed in the area chart, showing both the instantaneous and cumulative perspectives. The density matrix is generated as follows. First, a layout of the graph is computed using the Force Atlas 2 algorithm. Then, density matrices are generated at different resolutions. This is done only the first time the graph is loaded onto the database. This is a short demonstration of the compare task. All views are linked and coordinated in order to support the users in understanding even the small differences between each of the processes. This includes the behavior of the seed sets, but also the impact of the starting conditions. For the feedback task, the first question to ask is how to choose a good seed set. Our idea is to use visual analytics to modify the seed set selection. This is based on both the visual analysis of the global and local topology of the graph, with the objective of improving the average spread with little to no impact on seed budget, that is, the number of seeds. We also offer basic guidance in seed selection, with the basic assumption to move seeds from high to low coverage areas. We now show how we implemented the feedback task. In this example, we have 3 simulations. In the 2 above, the seed set has been calculated by the 2 available heuristics, while the one on the bottom has a seed set made up by randomly selected nodes. It is immediately evident the different seed distribution, especially by inspecting the local topology. We would like to improve the performance of the randomly selected seed set. To do so, we identify an area with very low coverage and ask the system to give us suggestions of which might be good node candidates. The suggested seeds are listed in descending order of degree, and vice versa when seeds are removed from a cell. Visualizing the local topology in this context helps in identifying the potential impact that adding or removing nodes has in the specific neighborhood. This process is repeated until the user is satisfied and is ready to relaunch the simulation. The system compiles a short report of the modification and new seed budget. It is possible to see that the user-defined seed set significantly improved the spread over the original. Let's now move to how we evaluated our system. First, we described the 2 case studies. We recruited 2 visualization experts familiar with the problem of influence maximization. We included in the system real graphs compiled from the subject research interests. Each graph had 3 preloaded simulations, one with a random seed selection and the other 2 compiled with the other available heuristics. The protocol for the evaluation was an interview with the training and free exploration and a final task of improving one of the preloaded simulations. We recorded and evaluated the subject interactions and impressions while using the system and the approach and results of the evaluation task. In the first case study, we propose a InfoVis co-authorship network. The study subject decided to refine the random seed selection, achieving a 52% improvement in overall average spread. The result was within 20% of the other 2 seed selection heuristics, but with a slightly smaller seed set. On the left is shown the seed distribution, with the area highlighting the majority of changes from the original top and the user-defined bottom. On the right, the heat map at the end of the diffusion process. Improvements are evident, especially in the highlighted area. In this second case study, we have a Bitcoin transaction network, with edges weight representing wallet-to-wallet trust. In this case, the subject attempted at modifying the seed selection of the single discount heuristic. The final spread was within statistical error, despite having more seeds than the single discount selection. However, it had still a higher spread than the high degree heuristic. On the left, as before, you see the comparison in seed distribution between the original seed selection on top and the user-selected seed set. The green square shows where the majority of the modifications happened. If we move at the end of the simulation, you can still see that while the overall spread remained basically the same, the user could achieve better coverage in this part of the network. For the second evaluation, we follow the IST protocol. This protocol identifies 4 higher-level visualization components that are confidence, essence, time, and insight. These are broken down into heuristics that are readable statements that embody the core concepts of the higher-level components. The experts recruited should assess on a Likert scale from 1 to 7 how the visualization or visual analytics system under test follows the heuristics, meaning that higher scores should align on more variable visualizations. By averaging the heuristic scores per component, it is possible to see that VAME ranks above the sufficient score of 5 across the board, thus suggesting a positive outcome for the evaluation. The standard deviation is more pronounced on the least ranked components. In conclusion, we show that VAME supports the analysis, comparison, and fine-tuning of influence maximization strategies. Also, during the case studies, we exposed and we showed how VAME supported different interaction workflows. We also believe, however, that other semantic information might support the users in the future, for example, providing new other graph attributes in the visualization. Visual and computational scalability deeply influenced many of our design decisions and still represent worthwhile future research directions. This ends this presentation video of the paper Influence Maximization with Visual Analytics. As this is a TVCG invited talk, the paper is already available and is open access. Here you also find the links to the code repository and to the replicability stamp. Please contact us if you have any questions and would like to collaborate on improving or using the system, and thank you for your attention.